Hello, my name is Meng. I'm a software engineer at Zoox. Today I'm going to talk about robust sensor fusion against on-vehicle sensor stillness. Sensor fusion is crucial for the perception system in autonomous vehicles. But sensor stillness, where data from different sensors arrive with varying delays, poses significant challenges. In this example, we have LiDAR and camera data well synchronized and spatially aligned. In the second example, LiDAR data is on time, but camera data is stale and causes significant misalignment. Here we define stillness, for example, for camera as Ts equals to T on time minus T current. T on time is the ideal camera's capture timestamp that should synchronize with the latest data from all sensor modalities received at the moment. T current is the camera capture timestamp of the most recent camera data actually received. Stillness can be larger or equals to 0. On vehicle, we have LiDARs and cameras synchronized and phase locked at 10 Hz. TC is defined as the camera capture timestamp. TL is the end of sweep LiDAR timestamp. In an ideal world without stillness, TC minus TL is well bounded between minus 0.1 second and 0 seconds. However, on the left figure, we observed out of distribution values, meaning stillness from real on-vehicle logs. So either LiDAR or camera can be still for one frame in this specific example. To solve this problem, we first add per point timestamp offset feature in training for both LiDAR and radar relative to camera. This is defined as TC minus TI, where TI is per point timestamp. This helps the model to learn stillness. Second, we simulate still sensor data based on profiles from real on-vehicle logs. We calculate the perfectly synchronized camera timestamp using pure geometry. We define the maximum jittering time difference and jitter a random timestamp to curate older or newer image data than LiDAR. And we repeat this similarly for radar. Third, we apply this still sensor data as data augmentation during training. We apply our method in a perspective view mid-fusion transformer-based detection model. 3 independent backbones extract LiDAR, radar, and camera features first. Then we dynamically fuse them and apply a dyno decoder head to output classes, 2D and 3D boxes. Here we compare two models, a baseline model trained with perfectly synchronized sensor data and a candidate model trained with still sensor data augmentation. We cross-validate them on 2 validation datasets, a perfectly synchronized dataset and a still dataset. Comparing experiment 1A versus 2A, the baseline model shows severe performance degradation across all classes when evaluated on still data. However, the candidate model in 2B maintains robust performance evaluated on the still dataset, and it learns to handle stillness and spatial misalignment among sensor modalities. What's more, for 1A versus 1B, the candidate model achieves similar metrics on perfectly synchronized data. Besides, our approach is model agnostic, easy to integrate, and has negligible impact on system latency. Thank you.